thanks to our current price, we got to spend a whole day on it. I don't think that's enough information. So I went on to D2L and put some tutorials on there. So if you go to D2L, you go to content, and then you go to exam materials, and then go to the study resources for exam 3. And then scroll down to where you get to tutorials. There's one at the bottom that says very good Vesper tutorials. That one is a whole little set of Vesper stuff. And the guy takes clay models and kind of puts them together, explains things. I really like that one. So it's a set of them. So let's say you're looking at the first one, you're like, I got this. Then you can just skip to the next one. I also found another chapter online that explains most of the stuff that we're going over right now. So that's under the tutorials. It's labeled Additional Reading Explanation, chapter from the book online over material. So that's just a separate chapter. If you don't like the one in our book, read our book, but then if you need more information, which you very likely will, that also has a lot of really good information. It's got a lot of good figures and things like that. And then I've got one on valence bond theory, which we'll go over today, and 2 more on Vesper. And then I have one on how to identify polar molecules. So that's where we're going to start today, is how to identify polar molecules. So in order to identify a polar molecule, you have to do a couple things. Can anybody guess what step 1 is?
Determine electronegativity.
It's been step 1 for. Huh? Say that again.
Determine electronegativity. Or
almost
bonds.
That's one of the steps. Amelia has it right that you've got to draw the structure first, and then once you draw the structure, then you'll look at the electronegativity, and draw the little arrows, and then you're going to take a look at the symmetry, and then you'll be able to tell. So, for example, let's say I'm trying to do CH4 to see if it's polar. No, let's not do that one. Let's do CH2O because I know that was nonpolar. So CH2O. All right. So first you count up how many valence electrons. So that's going to be carbon equals 4, hydrogen equals 1 times 2, and oxygen equals 6. And you add all that together and you get 12. So carbon goes in the middle. H, O. And it doesn't really matter too much how you set this up. Like, do you put the oxygen on top or the left? Doesn't really matter. So then I've used 6, leaving me 6. So I'm going to put them here, right? And then check to see if carbon has an octet, which it doesn't. So I'm going to borrow some of the electrons from the oxygen and make a double bond. And now it has an octet. Everything's all satisfied. So now what I want to do is I want to draw, I want to look and see which ones are polar. And one important thing to remember is that if you see this, that's always nonpolar, right? Always. So you can look at the carbon hydrogen and just go, not really polar, but you can still draw arrows for it, you know. But the main thing that we would be looking at is we're going to look for symmetry. And when I say symmetry, we're going to look to see if everything around it is the same. Well, I guess first you want to see if there's a polar bond. And obviously there's a polar bond right here between the carbon and the oxygen. All right, so the carbon is less electronegative, so it gets the plus end of the arrow. Oxygen's more electronegative, so it gets the arrow end of the arrow. So there's one polar bond there. And then we want to take a look and see if the whole thing is symmetric. By symmetric, what I mean is is everything all the way around the carbon the same? So it's hydrogen, hydrogen, so far we're good. Oxygen, oh, there's an oxygen there. It's not hydrogen, so that means it's polar. So that's kind of how you tell. Let me show you another one that's nonpolar, the one that we actually did in the quiz today. All right, let's see. It would, you could. It's nonpolar. So generally I just don't bother with those. But you could still draw an arrow for it. That's a good question though. So let's take a look at carbon dioxide. All right, so we've got the Lewis structure looks like this. All right, so I've got to figure out what's more polar, carbon or oxygen, not more polar, more electronegative, carbon or carbon or oxygen. Okay, got it. All right, so on the periodic table, we know it gets more electronegative as you go up and to the right. So there's going to be a carbon here and group 4, and then nitrogen is next, and then oxygen. So oxygen is more electronegative. So things that are more electronegative get the arrow end of the arrow, the pointy end. All right. And so it's going to go to carbon, which is less electronegative. All right. So in this case, you would maybe assume that it's polar because it's got 2 dipole moments. So these little arrows indicate a dipole moment. But there's a problem here, and that it cancels it out. I don't know if you've had physics yet, or if you've ever had to add vectors, but if you were adding a vector is like a magnitude with direction. So let's say there is a person here, and they travel like 3 feet this way, and then they travel 3 feet this way. Then the distance they've actually gone is not at all. They didn't really go anywhere. So those vectors cancel each other out. It's kind of like on a number line. You start at 0, and you've got +3, -3. So going left would be negative, and right would be positive. You add those 2 together, you get 0. And it's the same thing here, because whatever the dipole moment is from carbon to oxygen is the same for the other carbon to oxygen, because they're identical. So it's like adding +x and -x, and they just cancel each other out to be 0. So that means it's nonpolar. But it does have polar bonds. So it's possible to have a molecule that has polar bonds, but not be a polar molecule. Does that make sense?
Mm-hmm.
Yep. Okay. Cool. All right. So let's do another one. Correct. Because they're in opposite directions, it's nonpolar. Yes, they cancel each other out. So let's take a look at water. So water starts to, there are 2 ways to look at water. But first, obviously, we have to draw the Lewis dot structure. Actually, I'm going to draw it the other way. It doesn't really matter how you draw the structure of water. But let's say I drew it like this, right? It almost looks like everything cancels itself out because it's like everything is opposite. But this is where VESPER comes in because you need to know what the geometry is in this case. You don't really need to know it, but because I'll show you a shortcut in a second. But if you know what the geometry is, it kind of gives you an explanation of why it is polar. So if you're looking at this, we have two bonded atoms. So the atoms bonded is 2, and the lone pairs, we have 2 lone pairs. So the steric number is 4. So the electron geometry is tetrahedral, and the molecular geometry is bent. So what that means is you have the oxygen, and generally with something tetrahedral, it looks kind of like this, right? And so you've got an H here, and an H here, and then instead of little lines there. Oh, that's a good question. So to get the steric number, you just add the number of atoms bonded to the central atom plus the number of lone pairs, and that'll give you the steric number. That's a good question. So to get the molecular geometry, that's one of the things that you have to memorize. So there's a chart in the book, I think it's section 5.1. If it's not 5.1, it's 5.2. It's toward the bottom of that section, or if you're in a regular textbook, it's toward the end of that section. And there's a table that has all the angles and all the molecular and electronic shapes. So you want to memorize all of that. Yes, you will when you're doing the VESPER stuff. All right. So in the case of oxygen, of water, we have 2 lone pair. So now if we look at it like this, we can see, it's 5.2? Okay, that's good. Thanks, Caspian. So we can see that oxygen is more electronegative than hydrogen, right? And then the lone pair are more electronegative than oxygen because they're just electrons. So overall, you have this dipole moment that goes straight up through the molecule. Now here's the shortcut. And this almost always works. So we're going to go around the molecule and see if everything's the same, just like we did in the last one. Hydrogen, something different. It's polar. So let's try. I'm trying to think of a good one. I'll just make one up. All right. Any questions about this one? Hey, that's a good question. So the reason it's polar is because the electrons are going to flow toward the oxygen and then toward that lone pair. So overall, they're flowing in one direction, so nothing's canceling. And the shortcut is you can tell that that's going to happen on most molecules when you draw out the Lewis dot structure by going around the molecule to see if everything's the same. And if anything is different, then that would be polar. Yes, we can. Hunter, you have a question. What's your question?
So you have a dipole moment going towards the lone pairs. So it just always goes towards that lone pair, or how do you determine the direction? The direction is determined based on which one is going to be more electronegative, the oxygen or the hydrogen. Let's say we had something, you can't have this molecule,
But let's say we had this instead. Now, obviously, this is make-believe because hydrogen only makes one bond, and I have two, so this would never happen. So, but in this case, the arrows would point this direction, and that shows that the electrons are going toward the oxygen. And because they're all going in the same direction, which is away from the hydrogen, that's what makes it polar. If you had, sorry, I gotta add the lone pairs too. If you had something like this. Okay. If they're pulling in the same direction, it's polar. Sure, okay. So, and I'll show you a non-polar one in just a second, Erin. So this one is polar. The shortcut is you go around the Lewis dot structure, and so I'm going to say this is hydrogen, hydrogen. So far everything's the same. Lone pair, not same. So it's polar. So if everything all the way around it is the same, it's pretty much always non-polar. But if something's different, it's usually polar. So let me show you one more example, and then we'll talk about valence bond theory for a moment. They are the same on the top and the bottom, but when you draw the VSEPR structure, so when you draw the actual geometry of it, it turns out that the lone pair are on the top and the oxygen are below the oxygen. Okay. All right, so I'm going to, I'll probably make an additional tutorial or lecture or something like that to put on D2L for you guys. So I don't think I'm giving you enough information.
Yeah, you're not doing shit.
Somebody's unmuted and using foul language. Okay.
Muted.
That's okay. All right. All right. So let me show you one that's non-polar, and then we're going to go to the next thing here. Okay. So let's do CH4. All right. So we got CH4, and even without drawing arrows, I can tell this is non-polar for two reasons. One reason is because a carbon to hydrogen bond is not polar, and that's all the bonds we have. So that's not polar. The other reason is because if I go around the molecule, it's hydrogen, 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 everything is the same. So that makes it non-polar. So even if we had something that looked like this, Hunter, you still have a question?
No, sorry.
Well, that's okay. Chad, you have a question.
Yeah, so I thought like if it was in opposite directions, it would be non-polar, and if it was in the same direction, it would be polar.
Yes, that is correct.
Like in this case, it's different.
Say that one more time.
I said, like, how come in this case with the CH4 it's different?
Oh, okay. Because if you draw the tetrahedral structure for it, they're technically all at the exact same angle. So if you actually made a molecule and held it in your hand, as you rotate it, you'll notice that it doesn't matter which way you rotate it, it's the same. So all of these are, honestly, I don't know which one is more electronegative because of where hydrogen is. I think carbon is more electronegative. But anyway, whichever direction the arrow is pointed, they're all going to be opposite each other. They're all going to go in different directions. So kind of imagine the carbon as a knot on a rope. And this rope has 4 ends. And in this case, we have 4 identical people all pulling on the rope with the same strength. In that case, they're not really going to go anywhere, right? Oh, carbon is 2.55. Oh, cool. All right. I was right. All right. So they're all pulling with the same strength. They're not going to go anywhere. So in that case, if they're not going anywhere, then that would be an example of something that's nonpolar. In other words, there's no net movement of anything. So let's say instead of that, we have an enormous person standing here, and they're all 3 pulling as hard as they can. Do you think that the knot is going to go in any one particular direction? Assuming that the huge guy is really strong. Correct. It would go toward the huge guy. So since it's going in one particular direction, that's the idea of polarity, is the electrons all traveling in one direction. Not all traveling in a way so that overall nothing really happens, but traveling in a way so that the electrons all go one way together. All right. So I will go into more detail about this when I make the additional lecture. I'll probably post it this weekend. But maybe I'll have time to make it this afternoon. If I do, I'll post it early. That would make it nonpolar. So because the electrons aren't going anywhere in one particular direction, it's nonpolar. Yeah. All right. So now let's take a look at valence bond theory. Right? So with this, we get hybrid orbitals. For this stage of learning about valence bond theory, we're going to assume that all the terminal atoms aren't hybridized. And by terminal, I mean the ones on the outside at the end. So only the central atom is going to hybridize. All right. So our goal is to figure out what is the hybridization of these things. So to explain that, I kind of got to go over, well, what the heck? What is a hybridization? And then I'll give you a shortcut. And as long as you can count to like 6, you're good. Okay. And say the words S, P1, P2, P3, you know, et cetera, et cetera. Okay. So let's say we're looking at CH4. So it's tetrahedral. The angles are 109.5. If you just look at the Lewis dot structure, it looks like they ought to be 90 degrees apart, but they're not. Carbon will make 4 bonds, but if you look at its valence, It's, gotta look up a periodic table real quick. I know it's got 4 valence, but I want to get a little more information. Okay, so it's in second row, so we're going to be ending in the 2 P's. Okay, so carbon would be 1s2, 2s2, 2p2. So it's got a total of 6 electrons, and these in right here are valence. I know they're valence because they both have high N levels. So 2 is the highest, so we add them together. All right. So that would look like this. And then this. And then this. If that's the case, looking at this, to make a hybrid orbital, you've got to take one orbital, or to make a bond, you've got to take one orbital that has an electron in it, and another orbital that has an electron in it that can spin pair. Spin pair means one goes up, one goes down. That'll make a bond. Looking right here, we only have 2 orbitals that have half filled. So according to this, it would only make 2 bonds and not 4. But that's not how carbon actually works. So Linus Pauling kind of took quantum and Lewis dot structures and the Lewis theory and brought it all together and made a monster of the hybrid orbitals, which aren't so bad once you learn the shortcuts. But before that, you're like, orbitals everywhere, and it's no fun. So what happens instead of this is these actually hybridize. So they become sp3 orbitals. So you've got a 1s, and then 4 sp3 orbitals. And what's happening is your s orbital from the carbon is mixing with your p orbital from the carbon and making a Frankenstein orbital called sp3. And now we have 4 half-filled orbitals, and this explains why carbon will make 4 bonds and doesn't, in fact, make 2 like the Lewis dot structure would predict. So the Lewis dot structure predicts a lot of good stuff, but it doesn't predict everything, and it doesn't predict everything correctly. So that's why we went to valence bond theory next. So let's see. I will show you another one. I'll do NH3. Right. And then I'll show you the shortcut. All right, so that's NH3. That's a good question. The reason the 2s disappear is because the hybrid orbitals are always the valence orbitals, so it doesn't so much matter which energy level they're in anymore, because you're not going to have like 2 sp3, 3 sp3. The hybrid orbitals are always going to be the last ones, and so that's why they don't number them. That's a good question, though. All right, so looking at this, nitrogen has a total of 7 electrons. So it's 1s2, 2s2, 2p3. Okay, so it looks like it would only make 3 bonds. But as we can see here, this nitrogen could make 4. But if you have one S and then two S and then two P, according to Lewis, only those three could make a bond. But that doesn't happen most of the time with nitrogen.
Where's nitrogen?
Nitrogen usually makes about four. Well, it makes four, not about four. So what happens is you're going to get a combination of these. And again, you're going to get sp3. And here's the shortcut for this. You have to remember that it goes in this order: S, P, D, F, and that there can be up to 3 P's, and then 5 D's and 7 F's or whatever. And in this case, and there's really only one S orbital. When I'm putting these numbers up here, I don't mean that's how many electrons there are, that's how many orbitals there are. Right? So I'm going to start looking at this right here, and I'm going to say the letter S. I'm going to look at this one and say the letter P and the number 1. And then I'm going to say P and the number 2. So I'm going to change that to a 2. And I'm going to look at this, and I'm going to say the letter P and the number 3, and I'm going to change that to a 3. So that's the hybridization. So it's S, P1, P2, P3. So that's sp3. And I got 2 minutes, so I'll show you something else. There are only 4 electrons. Oh! You got me on that one. I'm going to have to actually look that up because I'm thinking that that should be this. Maybe I miscounted something. I don't know. I'll look at it and I'll send out an email. If I don't send out the email, it means I forgot. So send me an email and ask me, and I'll do that. All right. The last one I want to show you really quick is going to be another made up one. So let's say we have this. Okay, so I'm going to do the counting thing again. So I'm going to say S, P1, P2. We know there are, in fact, 3 P's, right? So that means this is going to hybridize, and there will be one leftover unhybridized p orbital. And the unhybridized p orbital is what causes the double bond, and the double bond is called a pi bond. No, it doesn't. You could start here and go that direction. It doesn't matter. So long as you count everything and you remember that lone pairs count. And that double bonds and triple bonds you only count once. So with the pi bond is formed by this unhybridized p orbital. Unhybridized p orbitals are the only things that cause pi bonds. Pi bond, so every kind of bond, single, double, or triple, has one sigma bond. Anything that's not that one sigma bond is called a pi bond. You can kind of remember it because first you have dinner and then you have pie. So dinner's kind of like the sigma bond. You've got to have that first. So it's sigma, and then whatever's not sigma is pi. So Summer, you're saying no. Oh, Natalie, you're saying, so what would that hybridization be? Do you mean the hybridization of a pi bond, or do you mean the hybridization of this molecule here? Oh, okay. That's going to be sp2. Six. But also, if you go to D2L, go to the tutorials. There's a lot of extra help there, like a lot of extra help. And there's a better chapter on it online. But it's chapter 6, and not chapter 6, it's chapter 5 in our book. Why am I saying 6? We're not in chapter 6. So it's sections 5.2 and 5.3. I think valence bond theory is section 5.3. No, section 3 and 4 today. And valence bond theory was 4, I think. Or was that polar molecules? I don't know. It's either 5.3 or 5.4. All right. And I've gone over like usual. I know I haven't gone into a lot of detail here, but I will go into detail. I'm going to make an asynchronous lecture, which basically means I'm going to make a lecture as if I was teaching class, but no one will be there. And then I'll record it and post it on D2L. You're welcome. And I'll go over all the stuff we did Monday and all the stuff we did today. And it'll probably be long. So fast forward through stuff if you already know what it is. You're welcome. And I'll take a look at that homework also. Bye, guys. I will see you Friday. Depends on when I get it done. If I get it done today, I'll post it today. If I don't get it done today, I will post it either tomorrow if I have time. But I've got a bunch of appointments tomorrow, a bunch of places I've got to meet people. And then Friday, I should have plenty of time. So if I don't get it posted today or tomorrow, it will definitely be Friday. But it will be before the weekend. And I will take a look at 5.1. Oh, absolutely. Yeah, I'll send an email when I get it posted. So you don't have to, if you don't see it by Friday afternoon at like 3 o'clock, go ahead and send me an email. If I haven't already sent you one saying I'm posting it this evening or something, then like if I send out an email Friday saying I'll post it at 5, then you know it's coming at 5. But if you don't see it early in the evening on Friday, make sure you email me so that I can check on why it's not showing up or whatever there. Okay. All right. I will see you guys later. You guys are awesome. If you're a little confused, don't stress over that. I will unconfuse you before Saturday. Hey guys.